Hi, my name is Yusuf, and today we're going over lab pore oscillations. Introduction. The main purpose of this lab is to study the motion of a spring mass system that swings in an arc while oscillating vertically. We aim to compare the experimental motion captured in video with a computational model that simulates the same system. Our goal is to determine how well the energy is conserved during the motion and how accurately we can predict the system's behavior using our model. The system is modeled using key principles of energy conservation, focusing on the changes in kinetic energy, gravitational potential energy, and spring potential energy. By analyzing the motion using video tracking and coding, we're able to predict the path and energy changes of the mass over time. So here's a preview of our main results. The computational model aligns well with the experimental data, matching closely the motion in both the x and y directions. Energy is conserved throughout the model, with no fluctuations observed. When comparing the oscillation periods derived from the x and y positions, we find them to be nearly identical, reinforcing the accuracy of both the model and the experiment. But we find minor deviations in the predicted and observed data. These can be reasonably attributed to external factors such as friction and drag. So now onto the actual experiment. The system was our object, the spring, and the earth. The surroundings were none, so we can assume that the work done on the system is zero, at least in theory. The object was attached to the spring and pulled back to the left slightly and raised from the equilibrium point. The position is negative 0.114, comma negative 0.643, comma 0, where 000 would be the spring's origin up here. The mass is 0.402 kilograms. The spring constant is unknown and will need to be solved for after the experiment is finished, and the relaxed length will need to be calculated after the spring constant is solved for. So the object is let go and left to oscillate. The position at different periods of time was recorded and plotted using tracker. So we use code to model the experiment and plot both the observed and modeled experiment data together. So this is an initialization stage of the graph where everything's created. And this is the system properties and initial conditions. So first off, we have the ball's mass. Then we have the initial position and initial velocity, which is 0. And then here's our initial time and the change in time that we will be recording our data. Over here is our constants and energy calculations. So first we have the gravitational constant, which is standard on Earth. We have the spring constant, which we calculate using the period. We use the equation 2 pi root m over k to solve for k, because we have this from our experiment, which we found to be 1.519 seconds. And then similarly, we use that value of k, we plug it into this equation, which represents our initial stage before the ball was lifted and left to swing. So that leaves us with our rest length being 0.127 meters, which we input here. And here is just the spring variables based off of this equation. And this is the energy equation, so half mv squared, mgh, half ks squared, and then total energy is all that added up. Here's our update loop where we define our initial energies. Here's our gravitational force, spring force, total force, which is these two added up. Then we update the ball's velocity with the velocity update formula, and same with the object. And then down here we update the spring. And over here we calculate the energy changes by, after our velocity and position are updated, we redo the equations and then calculate the change based off of the new variable minus the old variable. So we do this for kinetic energy, gravitational potential energy, and spring potential energy, and total energy. So after that, this is just plotting everything. And here are our models. This is our predicted energy change versus time. As you can see, the changes in spring potential energy, gravitational potential energy, and kinetic energy all even out, such that the total change in energy remains 0 at all times. And here's our observed position data. As you can see, it's oscillating back and forth in both the x direction and in the y direction. And here's a comparison of our observed and modeled data. As you can see, it's closely related, though there are slight deviations. And we can explain this by going into our discussion. One important source of error is that the spring in the system is not perfect. In reality, some energy is always lost due to heat as the spring stretches and compresses during motion. This means that energy isn't fully conserved, which would explain some of the fluctuations in our energy plots. Additionally, we need to consider air drag. Even though the effect might be small, drag acts against the motion of the mass and gradually slows it down. This also causes some energy to be lost from the system. When it comes to calculating the period, there's another limitation. We use position data from 2 points to estimate the period, but because the data is based on discrete video frames, we're not capturing every single moment. This means that we might not have measured the exact position at the true period, since we're only getting snapshots of the motion between frames. Now for the conclusion questions. The energy principle is completely satisfied in the system, as we see that the total energy remains constant throughout the motion. The changes in kinetic energy, gravitational potential energy, and spring potential energy balance out each other. And for our second question, our oscillation period that we observed from the x data was 1.5 seconds, and the period from our y data was 1.41 seconds. When we calculate the periods of oscillation separately from the x and y system data, we find that they're very close to each other with a difference of only 0.09 seconds. The reason the oscillation periods in the x and y directions are so similar is because the two motions are coupled. The object swing and the stretch of the spring are both driven by the same restoring forces, which are gravity and spring force. These forces act together to create an overall periodic motion, which explains why the periods are nearly the same. Small difference between the x and y periods can be attributed to a couple of different factors. The first being the swinging motion is influenced slightly by the horizontal displacement, which may alter the period slightly compared to the vertical motion. The imperfections in the spring or small amounts of air drag could also cause the two periods to differ slightly. Finally, as mentioned earlier, the data is collected frame by frame, so we're not capturing the motion continuously. A slight timing difference could lead to small variations in the periods. Thank you.